Okay, fine. So I have to accommodate for the change in the internal energy. So you have three variables P, V and T. Why did I choose V and T? I have chosen V and T for a particular purpose. The reason for choosing V and T is that del U del V at a constant temperature, or del U del V or del U del T, I have to have subsequent expressions for that. Keeping volume and temperature variable is the easiest option for me because they are easily controllable rather than pressure. Also, we'll see why there's a why this combination is preferred. So if I do over here, if I take a complete differential here, I will have del U del V at constant temperature dV plus del U del T at constant volume dt, right? So this is what I have. So now look at these expressions. This path has been taken where your temperature is constant, and this is where the volume is constant. So for this path, this takes care of your U2 minus U3, change in internal energy, and this takes care of this path where you have U3 minus U2. Do you understand now why you have written in this form? So del U del T at constant volume dt is U23. Here the internal energy change at a constant volume. I'm sorry. The change in internal energy at a constant value. This path. This is U221. U322. Yes. This one. Here the volume is constant. The internal energy changes because there is a change in temperature. So U221 is being accommodated over here, and for this path 3 to 2 I have del U del V, there is a change in volume at a constant temperature. So your pressure and volume are variable, right? So if I just substitute these two, what will we have? We have from here a measurable quantity del U del T at a constant volume dt. This is a measurable quantity. We say CVDT. Just open the earlier lectures, you will find that del U del T at constant volume is CVDT, and del U del V at constant temperature dV. I don't know this quantity actually. I don't know what it means, del U del V at constant temperature. So let's keep it in this way. So if I just write the equation again, so what we have is finally is CVDT plus del U del V at dV at constant temperature is equal to PdV, or you say minus PdV, del W was there. Okay, so this is the equation. Now consider this. We say that the internal energy for an ideal gas is only a function of temperature. If it is only a function of temperature, which happens to be an ideal gas, so del U del V at constant temperature dV, so U is not a function of volume. So del U del V becomes 0. So what you have, if I don't have this term anymore, so I have CV dt is equal to PdV. This is very important. Okay, so now this is easily integrate. We can easily integrate this equation. So I just can replace everything. CV dt is equal to nRT by V dV. You can have this dt by t over here. CV integration t1 to t2 the integration here, v1 to v2, nRT is constant, so nRT dv by v, so which will take the final shape, which will be CV ln T2 minus T1 is equal to nR ln V2 minus V2 by V1, ln V2 by V1. Okay. So if I just take this negative terms over here, so it will become nR ln V1 by V2. Okay. So CV ln T2 by T1 is equal to nR ln V1 by V2. So this gives me an expression from which, by substituting, I have T2 by T1 is equal to V1 by V2. Normally it's written as CV, and here goes the R, right? So it's written as a term gamma, and which can be easily replaced by it. So T2 by T1 is V1 by V2 R by CV normally we have this substitution, and finally we arrive from here PV to the power gamma equal to constant. You just substitute pressure and temperature and put it any variable. Normally it's written as gamma, CV1 is here. So this is an expression of pressure and volume for an adiabatic process, reversible adiabatic process. Okay, fine.